On the Blackboard Learn, you have this. Did anybody take a look at that? Keystrokes for you to find the root of the problem where you're solving for 10 to the minus 0.485, or in other words, so the constant k is this number, 0.32734. So you're solving for the function of z equal to that constant 0.32734 minus the z square root of 1 plus z divided by 2. This was what we set up last time. Divided by 2 minus z, all to the 1/2 power of 3 divided by 3 plus z over 2. This is how to do it with the TI-30 calculator. Right? So Jeffrey, you help me on this. Hit the second key right there, followed by this key, and then 0.32734. You get the picture there, right? And then you have subtract. So this sign right here, subtract. And then this gets the variable x right there. X or z. You can put x or z. I wrote z to be consistent with the book, but it's easier to put x there. And then you do the second, which is this one, on the to get the square root right here. And then you put 1 plus x divided by 2. And then this little button right there, this one, gets you outside of the parenthesis on the square root. So now you just kind of got outside the parenthesis on that square root. And now you can divide, then have a parenthesis, that's right here, right there. 2 minus x, close parenthesis. And then the second again, I should erase some of these things because you see all the keystrokes. The second, square root. So you're starting this square root right here, this 1/2, right there. 3 divided by, etc. And then when you hit the enter, you can put in the value 0.3 and run it and look at the answer. Then you can put in another value. Hold it. This is entering 1.41, enter and run, 0.478, and then the last one that I ran last time, 0.4685, and this is what was showing on the screen at the end. And so if you evaluate that function where z is 0.4685, that's the root. You solved it. I showed it to the AM class. There's another student, Song Yong. I butchered his name. And he said, fewer keystrokes. I don't know. This is not my calculator. So I'm going to post this PDF up there too. So did he get that off of you, Jeffrey? He was going to look for you to see about this emulator. Oh, that's why he called me. Huh? That's why he called you? Anyway, here's another set of keystrokes for the same calculator. And I think this time, he just did a run or a solve, and then it finds it right away. Last time we set up this problem, we were working through it, right? So we had methane, it burns with 90% theoretical air to form an equilibrium mixture of CO2, CO, H2O, H2, and N2 at 1200 Kelvin and 1 atm and determine the equilibrium composition. So what we did was we first set it up for 100% air, and that is CH4, that's the methane, plus 2 O2 plus 3.76 N2s, go to 1 CO2 plus 2 H2Os plus 7.52 N2s. But now we modify it or rewrite it for the 90% air, CH4 plus 0.9 times 2, so that's the 90% theoretical error, O2 plus 3.76 N2. You could write this as 1.8 O2s, but whatever. Then it goes to, we don't know how much CO2, we don't know how many moles of CO, we don't know how many moles of H2O, we don't know how many moles of H2, but we do know that it's going to have 6.768 moles of N2. So the unknowns, you can introduce different like X and Y and Z and P or whatever, or you could just, what I did was I said the unknown amount of CO2, the unknown amount of CO, the unknown amount of H2O, and the unknown amount of H2. So we have 4 unknowns, the amounts of those 4 entities in equilibrium. We do a carbon balance, and we find that on the in there's 1 carbon, on the out there's 1 carbon for every kilomole of CO2, and there's 1 carbon for every kilomole, or 1 kilomole of carbon for every kilomole of CO. Then we do the hydrogen balance. We find that there's 4 coming in with the fuel. There's 2 hydrogens for every mole of H2O, and there's 2 hydrogens for every mole of H2. Then the last one, the oxygen balance. So we had 1.8 times 2, so 3.6 oxygens coming in, and we had 2 for every mole of CO2, and 1 for every mole of CO, and 1 for every mole of H2O. I pause. Did we get those correct? Yeah. They look good? Then you just have to introduce, you want to collapse. I know by hand you want to be able to collapse it down to maybe instead of 4 equations with 4 unknowns, 1 equation with 1 unknown. So we introduce Z is equal to the amount of CO. So then you can rewrite this first equation right here. So the amount of CO2 is equal to 1 minus Z. And then once you've done that, you probably can come to this equation next. And you can rewrite that the amount of H2O is equal to 3.6 minus 2 times the amount of CO. Oh, that's 1 minus Z. Minus 1 times the amount of CO, that's Z. So you simplify and you find that the amount of H2O is 1.6 plus Z. Do you agree? And then you could come back to this equation and you'll find that the number of moles of H2 is equal to 0.4 minus Z. We stick them into our chemical equilibrium equation. Let me make room for that. So we have K is equal to the number of moles of CO, number of moles. I forgot to write down the reaction equation, didn't I? Well, last time we identified the reaction equation of interest is the CO2 plus the H2 goes to CO plus H2O. You have to pick one that's in the textbook in the table. That one fits the bill. So the number of moles of CO, number of moles of H2O divided by the number of moles of CO2, number of moles of H2. What about this term over here? Well, that exponent, nu sub C plus nu sub D minus nu sub A minus nu sub B is 0. So that just is 1, multiplied by 1. So we want to substitute at this temperature. We look up and we have 10 to the 0.135 is K. And then we're going to have Z for the number of moles of CO. Number of moles of H2O, we substitute 1.6 plus Z divided by the number of moles of CO2, 1 minus Z. number of moles of H2, 0.4 minus Z. I know that you can do some more algebra, but at this point I think sometimes you have to solve this equation with the calculator like we just did, and you can still solve this equation with the calculator, even though you could probably go further by algebraic manipulations. You could probably get this as a simple quadratic. Okay. So when you solve for this one, you find that, I'm going to have to scroll down, you find that the solution Z is equal to 0.1581. Hence, the solution number of moles of carbon monoxide, 0.1581 kilomoles, right? And then you can get the number of moles of the other ones using those equations right here. So it's number of moles of CO2 is 1 minus Z. Then the number of moles of H2O is 1.6 plus Z. And the number of moles of H2. Let me see if I have my notes that will give you the answers for those. 0.842 H2O is 1.758. The number of moles of H2, 0.242. The number of moles of N2, 6.768. If you do the mole fractions, this is 69.3%. For the H2, it's about 2.5% mole fraction. For the H2O, 18.0%. For the CO2, 8.6%. And for the CO, 1.6%. Equilibrium flame temperature. Well, before we had what we called the adiabatic flame temperature. So you brought some fuel, some source of oxygen, and you put it into a reactor, and that reaction, chemical reaction, was adiabatic. There's no heat transfer, and you came out with some products that were very hot, high temperature. So we talked about the adiabatic flame temperature. And we actually made some calculation, but then we went out and compared it to reported values, and reported values were lower than the adiabatic flame temperature. And one of the reasons was that we didn't account for any decomposition of some of the products. Now we have the tools that we can actually do that. I didn't say it's easy. I just said you have the tools to do that now. Okay? So let's set up and solve a problem to calculate the equilibrium flame temperature, which accounts for some dissociation of CO2 back to CO and O2, and it could also account for some H2O dissociating to H2 and some HO or some other H2O. You know what I mean? You can different amounts of what you model for dissociation. You could have a more elaborate dissociation model than maybe the simplest one. So carbon monoxide at 298 Kelvin, 1 atm enters a well-insulated reactor, and it reacts with 100% theoretical air, entering at 298, 1 atm. An equilibrium mixture of carbon dioxide, carbon monoxide, oxygen, and nitrogen exit the reactor at a pressure of 1 atm. For steady state operation and negligible effects of kinetic potential energy, determine the composition and temperature of the exiting mixture. So it's in equilibrium. So the composition is you're going to have to consider the chemical reaction or equilibrium. What type of equation will that look like? It'll look like K equal to these amounts to some exponents, and then amounts to some exponents divided by amounts to the exponents, pressure over the total amounts to possibly some exponents, right? That's our standard approach. But last chapter, we also, when we wanted to calculate temperatures of products, we had a different type of balance. We had an energy balance. What did that equation look like? it looked like something like, well, Q dot out or in divided by N dot F. Oh, it's a insulated reactor. That term is going to be 0 on the left-hand side. And then we had the sum of the stoichiometric coefficients times the molar enthalpies over all the products minus the sum stoichiometric coefficient molar enthalpies over all the reactants. Does that equation look familiar to you? Now you bring both of those to bear to calculate the equilibrium composition, which is going to be temperature dependent. Why is it going to be temperature dependent? This K is a function of temperature. So the higher the temperature, typically the way they write the equations, the more forward the reaction is, the more things that are on the right-hand side of that chemical equation are in the equilibrium mixture. There's more dissociation at higher temperatures. And that temperature is solved for with the energy equation. But to solve for the energy equation, what do you have to know? The amounts of each component that's going out in the products. But guess what? These are the amounts that are in the products. So they're tied together. They're coupled. And they're nonlinear. Let's go ahead and set it up. So what you have to understand is you write down the reaction equation. So we're going to have carbon monoxide and air, O2 plus 3.76 N2. Goes to, let's write it down for complete combustion. Okay. So you would go to CO2, true? That's finishing the carbon balance. And then there's no hydrogen. What about the oxygen balance? It looks like we need only 1/2 O2. Is that true? And then we finish it out by 1.88 N2s. True? But if we have some, it's 100% air, so we're going to leave the left-hand side alone. CO plus 1/2 O2 plus 3.76 N2. But instead of coming out with just all CO2, you can come out with some CO2 and some CO and some O2. But you're always going to have the 1.88 on the N2. Make sense? So we're going to be looking for that amount of CO2 in equilibrium, the amount of CO in equilibrium, and the amount of O2 in equilibrium. So we write down our reaction equation for the dissociation of CO2. We've done it before. What's the oxygen balance look like? How many are on the ins coming in? This is all the in, right? It's 2. Very good. And then on the outs, it's equal to, it'll be how many CO2s go out times 2. Because every CO2 has 2 oxygen. And then how many COs go out times 1 plus how many O2s go out times 2. Does that oxygen balance look good? Then the next balance, carbon balance. Okay, how many carbons come in? 1. How many go out with the CO2? And how many go out per CO? Good. Do we have a hydrogen balance? No, and the nitrogen are already balanced. So I have, this is one equation, second equation, and our chemical equilibrium equation, maybe I'll write it up here, is the K, which is 10 to the, you look at, well, we don't, it's going to be a function of temperature. I need to know it's a function of temperature, but we'll leave it, we just know it's a function of temperature. A lot of times you write it like this, K sub T, to emphasize it's a function of temperature, is equal to the amount of CO to the 1 power, the amount of O2 to the 1/2 power. You have the amount of CO2, and then you're going to have P divided by, and then you have the N total all to the 1/2 power. And what was that N total? It was the amount of CO2 plus the amount of CO plus the amount of O2 plus the amount of N2. Right? Okay. Well, at this point, there's a couple ways you can do it, but you're stuck with having to iterate. And if you wanted to iterate by hand, it would be very tedious. And if you wanted to iterate with the computer, well, then you would need even more than your TI calculator, because you have to be able to, given a temperature, get the equilibrium constant for that reaction. Put it down to where you have only two equations and two unknowns. The two equations will be the chemical equilibrium equation and the energy balance equation. And the two unknowns will be the temperature and maybe Z, which is the amount of CO. All right. But you'll still be stuck with two equations and two unknowns, and you'll have to then iterate to solve it. Let's go ahead and write down the energy equation. So we already wrote down that 0 is equal to the sum of those coefficients times the enthalpies over all the products, minus the sum of n enthalpies of all the reactants. So for each of the product, write it down. Let me scroll down some more. You have to write it down for which is one of the products, CO2 as a product. And then what's another product? CO as a product. And then another one is O2 as a product, and N2 as a product, right? And then we have the negative of all the reactants. So we subtract off, what's one of the reactants? CO as a reactant. This is confusing. You say CO and CO. I know, but it's on both sides. CO as a reactant, CO as a product. Then we have minus, what is another reactant? Is it O2? And then that's confusing because they say O2 is a reactant, O2 is a product. And then the last reactant, and it's not really much of a reactant, is N2 as a reactant. And you say, come on, how come I have N2 on both sides? Well, that's the way it is. So each one of these terms has an N, then it has this enthalpy on a molar basis. It starts with the enthalpy of formation, doesn't it? And then it has the molar enthalpy at the product is going out at that equilibrium flame temperature minus the enthalpy at 298, the reference temperature. Close paren. So we have the unknown amount of CO going out in the product. This was the unknown amount of CO2 going out in the product. The enthalpy of formation of CO going in the product, plus the molar enthalpy is a function of the equilibrium flame temperature minus the enthalpy at 298. Then you have the equilibrium amount of O2 going out in the product, enthalpy of formation, minus enthalpy at equilibrium flame temperature, enthalpy at 298, molar, close paren. This is a plus right there. That's right. Is that right? Is that what you're asking about? Okay. And then this is the nitrogen in the products, and then the enthalpy of formation plus the enthalpy of nitrogen at the equilibrium flame temperature minus the enthalpy of nitrogen at 298. And then down here for the carbon, so what is the amount of the carbon monoxide coming in? Wasn't that N of 1? So let's put that one in right away. It's the number. Okay, fine. Put the number of moles of carbon monoxide in the reactants coming in times. Then we'll have the enthalpy of formation plus the change in H. Well, this is delta H. This delta H bar for carbon monoxide, it comes in at 298. It comes in at standard conditions, so the delta H is 0. Okay. Let's continue to work over here. The number of moles of O2 in the reactants, enthalpy of formation of the O2 plus delta H bar of the O2. Well, delta H bar comes in standard condition, and what is the enthalpy of formation of the O2? 0. And so the same thing applies for N2 of the reactants. The enthalpy of formation and the delta H bar are both zeros. Okay, let's take a look. This enthalpy of formation is also 0 for the nitrogen in the products and also for the oxygen in the products. True? But if you want to, this number is 1. And then what is that enthalpy of formation for the carbon monoxide? Negative 110,530. You look it up in the table. Enthalpy of formation of the carbon dioxide going out, negative 393,520. And the enthalpy of formation is negative 110,530. So you have to know or have a guess of the temperature of the equilibrium flame temperature in order to evaluate these delta H's to find out if that is equal to 0. This all has to equal to 0. And these are unknown as well. So those are the two big equations, the chemical equilibrium equation and the energy equation, with the temperature and the amounts unknown. Well, let me give you some numbers for the answer on this one. It's 2663 Kelvin is the adiabatic flame temperature, accounting for none of the dissociation of CO2. But if you account for the dissociation of CO2 using the information that's in the table for that equilibrium constant as a function of temperature, the temperature comes right in at 2400 Kelvin. That's how much of a drop there is, just accounting for dissociation of CO2. And that Z, the amount is 0.125, meaning this is 0.125. It's quite a bit of carbon monoxide going out at that elevated temperature because of the dissociation. All right? And then this number, for the number of moles of CO2, instead of being 1 like it was before, it's 0.875. And this is 0.0626. Let's talk about simultaneous reactions, because typically you also, if you have CO2 present, you may also have water present. And if it's an elevated temperature, the CO2 can dissociate, so can the H2O. In general, they have multiple reactions instead of just A and B going back and forth between C and D. You could just continue it. There's E, there's F, there's G, there's H, right? So you could have two reactions going on at the same time. Not only that, but maybe this E is the same as that A. Maybe they're the same. One or more of them could be the same in the equilibrium equation. So don't lose sight. For each one of these, you'll have an equilibrium equation like K for the first. How's that? This would be the first reaction, RXN, is equal to, and then you have your formula like the amount of A, like n sub C to the nu sub C, n sub D to the nu sub D, right? divided by ... And then you'll have the equilibrium constant for the second equation. And it's going to be some nu sub g, n sub g to some nu sub g, n sub h to some nu sub h divided by... Now let me go ahead and do this. Let me write it as if there's an a here. So it would be n sub a to the nu sub a in the second equation. There's a nu sub a in the second equation. And this would be nu sub a in the first equation. Up here, finishing out, that we'd have n sub a, the same amount, to the exponent nu sub a in the first equation. I don't think it's that overwhelmingly difficult. You just have to think about it. Okay? And then you would have the amount of f to nu sub f, and the amount, this is an amount of b, to b, and this is the amount of f to nu sub f. All these are pressure over the 1 atm reference pressure. Pressure over the 1 atm reference pressure. But now we have the sum of the n's, the total amounts there. And that n is the same as that n, and that n is the amount of A that's present in the mixture, the amount of B, the amount of C, the amount of D, the amount of F, the amount of F, the amount of G, and the amount of H. And if you had an inert, put that in too, because all of those are in equilibrium. All right, and then you have the possibility of that exponent being non-zero. Here it would be nu sub C plus nu sub D minus nu sub A1 minus nu sub B. Here it would be nu sub G plus nu sub H minus nu sub A2 minus nu sub F. Did that framework look good? And then you can solve. These would be a function of temperature, and if they're in equilibrium, they have the same temperature. It's not like this reaction can be going at a different temperature than that reaction at equilibrium. They would be the same temperature. Should we set up a problem? So we have 1 kilomole of CO2 and 2 kilomoles of oxygen and 2 kilomoles of nitrogen. They flow into a reactor, and an equilibrium mixture of CO2, CO, O2, N2, NO exit at 3,000 Kelvin and 1 atm. You kind of go slow. We have 1 kilomole of CO2. We have 2 kilomoles of oxygen, and we have 2 kilomoles of nitrogen. They flow into a reactor, and what flows out is an equilibrium. And we don't know how much CO2 flows out. We'll leave that as an unknown. We don't know how many moles of CO flow out. We don't know how many moles of O2 flow out. We don't know how many moles of N2 flow out. And we don't know how many moles of NO flow out. So how many unknowns are there? 5. 5 unknowns. The temperature's given, 3,000 Kelvin and 1 atm. So you're going to ask for the equilibrium composition of the exiting mixture. It's in equilibrium, so it's an equilibrium composition. What you have to do is you have to find 2 reaction equations out of our table in our textbook that link these 5 together. Well, one you're very familiar with, right? CO2 disassociates to CO plus 1/2 O2. That's one of them. And that, links this one, and this one. True? But there's another one. I don't have the book in front of me. Can you look at the book and see which one it is? Yes. So 1/2 O2 plus 1/2 N2 goes to NO. That'll link them together. Neither of these have H's in them, and there's no H in this whole problem. No hydrogen, right? So those are the two that you need. Now, you can look up the K for the first reaction at 3,000 Kelvin. It'll be 10 to the minus something, or plus something, I don't know. 10 to the minus or plus some component, 0.485. And then what about the second reaction? Negative 0.913. I think if you run the calculator, this becomes 0.3273. This becomes 0.12218. So that's our equilibrium constants, K. And so we have to get now an equation so that this is K for the first reaction, K for the second reaction, So K1 is equal to the amount of CO square root of the amount of O2 divided by the amount of CO2. Then we have the pressure divided by 1 atm. Well, it's 1 atm pressure, so it's 1 over 1. We'll just put it 1 there. Then we have the total amounts, N, which is the sum of all of those 5 components. And this one's raised to the 1/2 power. And then the second equilibrium equation, the amount of NO divided by the square root of the amount of O2 times the amount of N2. That look good? Yes, sir.
How do you determine the exponents one more time
on this one?
Yeah, and the one.
Okay. Yeah, it's going to be this plus this minus that.
And then
so it's 1/2.
So the amount is just the coefficient?
Yeah, this N right here is going to be the number of CO2 plus the number of CO plus the number of O2 plus the number of N2 plus the number of NO. So I don't know any of those 5, hence I don't know N either. Well, when you look at this exponent up here, it's 1 minus 1/2 minus 1/2. It's 0. Hence, all of this is just 1. So that simplifies the second equation. But you're still left with a nasty equation. And at this point, we have to get 3 more equations. One is going to be the oxygen balance equation. One is the carbon balance equation. And one is the nitrogen balance equation. For the oxygen, it's 5 coming in. And we're going to have 2 for every CO2. We're going to have 1 for every CO. We're going to have 2 for every O2, and we're going to have 1 for every NO. All right, how about the carbon balance? 1 in. We'll have 1 for every CO2. We'll have 1 for every CO. And that's it. How about nitrogen balance? 4. It'll have 2 for every N2. Have 1 for every NO. For the oxygen, you got right here, what is that? 4,
And then you have
5, 6. You're absolutely right. 6, right? So it's 6 on the oxygen, 1 on the carbon, 4 on the nitrogen. All right, so now I have the 5 equations, and you do have 5 unknowns. They're nonlinear. You have to use root finding numerical scheme. All right? Next time we'll pick up with phase equilibrium. So we're done with the chemical equilibrium. Thank you.